So in our first video, we talked about what is a differential equation and what does it mean to find the solution to a differential equation. In this video, we're going to explore slope fields, but before we do that, let's actually backtrack to something that we know how to do that we've done already this year. So we have worked with differential equations, and if we consider this equation that y prime is equal to 2x plus 5, we can find a solution to this equation by finding its antiderivative. So let's start off with finding y, the antiderivative of y prime. So we know that if we were to integrate 2x plus 5 with respect to x, we would get x squared plus 5x plus c. And we said that plus c is really important when we don't have limits of integration. We call that c our constant of integration. And therefore, there are really infinite antiderivatives to y prime, because c could be any constant, any number. So sometimes the way we will show this notation is I can show that I'm taking the antiderivative of both sides of the equation. And again, we said we would get this general solution or general antiderivative to our original equation. But something we have done already this year is we have found an antiderivative that satisfies a particular condition. Sometimes we'll call that an initial condition. So let's say that, let's see if I can get my pen to work. Let's say that we have the initial condition that the ordered pair 0, 4 must be on the solution to the differential equation of y prime. So what we could do is substitute the 4 for y. So we're using this antiderivative of y, and the 0 for x. So 4 is 0 squared plus 5 times 0 plus c. And when we substitute that ordered pair in, we could solve that and get that, sorry. I'm holding my computer vertically, so it's hard to write. 4 equals c. So now we could write the antiderivative as y equals x squared plus 5x plus 4. And so this is what we're going to think of as a particular or a specific solution. Whereas when we left our antiderivative with c, just standing in for any constant of integration, that's a general solution. Oh my goodness. Sorry, this is a learning experience. General solution. So again, this particular solution, it's specific to this initial condition that the ordered pair 0, 4 is on the solution. Initial condition. Okay, so with that in mind, we're going to talk about slope fields. So a slope field is a visual representation or picture of the possible solutions to a differential equation. Each sample point that we'll plot is going to be a small line segment that displays the slope that we would expect at that point on the curve. So in this table, we're first of all going to use this equation. We're going to consider this equation. Dy dx is x plus y. And this is actually not a differential equation that we would learn to solve in this class, but we can imagine what its different solutions look like using a slope field. So in this table, I'm going to draw a table to represent what the slope is at any ordered pair x and y. So this first box that I'm going to just highlight green for the sake of drawing attention to it, that represents the ordered pair -2, 2, and I could figure out what the slope must be of the solution of this differential equation by plugging in -2 for x and +2 for y in solving for dy dx. So if I plug those values in to dy dx, -2 plus +2 we know is 0. So as we go through and fill out this table, -1 plus +2 is going to be a +1, 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4, and so on. So I'm going to go through and fill out this table real fast. -2 plus 1. And you'll notice a pattern emerging on this one. Like we can kind of start to do this quickly. So that's going to be a -2, a -1, a 0, a 1, and then a 2, a -3, -2, -1, 0, and 1. And then lastly, a -4, -3, -2, -1, and a 0. So this table is just giving us, let's see, I think 25 values of dy dx. So the way to now turn this into what we call a slope field is we're going to go over to this graph that's at the right. And for example, at the point -2, 2, I'm going to pick a color that'll stand out bright on our graph. So at the point -2, 2, I would expect any solution that goes through this point to have a slope of 0. So I'm going to draw at that point a little horizontal segment that has a slope of 0. And in fact, what I think might be easier is to go through and plot all of the zeros first. So at the point -1, 1, I'm going to also expect a 0 there. At 0, 0, I'm going to expect there to be a slope of 0. At the point 1, -1, I'm going to expect a 0. And then at 2, -2, I'm going to expect a slope of 0. All right, so we basically just plotted all of these zeros. All right, I think I'm just going to go across the first row. So as we move across the row, so at the point -1, 2. So at -1, 2. I'm going to expect the slope of this to be +1, and I don't need to make my line segment perfect, but I do need it to be approximately a slope of +1, so I might do +1 like that. At the point 0, 2, I'm going to expect the slope to be steeper, so I might show that it's steeper. At at 1, 2, I'm going to make it even steeper. And at 2, 2, I'm going to make it really steep. So it's not necessary to make those line segments perfect, but we do want to show that it's getting steeper or less steep somewhat appropriately. All right, so then if I go to the ordered pair -2, 1, so at -2, 1, that's going to have a slope of -1. So however steep I made my slope of +1, I want my slope of -1 to be about the same, but going in the negative direction. So then as we move over, we could plot the rest of these slopes. So at 0, 1, that's again going to be a slope of +1. And then it gets steeper, and then it gets steeper. Oops, it's kind of hard to do. All right, then let's see at -2, 0, so on the axis for these, we're going to have a slope of -2, so it needs to be steeper, steeper than our slope of -1. And then we'll have our slope of -1 here, so it should be about the same. 0, +1, and then it gets steeper after that. You know, it's really hard to do these to make them look appropriately steep. All right, 2 more. So from, let's see, at the point -2, -1, that's going to be steeper. In fact, I'm just going to go ahead and do the one below it to make sure that I get an even steeper line. All right, so at -2, -1, that little line segment is going to have a steep slope of -3, then a little less steep over here, a -2, then a less steep over here, a -1, then our 0, then our +1. And then that last row, -4, -3, -2, -1, 0. All right, so that is how we can sketch a slope field. I know it's hard, like when the numbers get really large, it can be really tough to make each one look steeper or less steep than the one before it. But you might have already noticed in our spiral on page 114, there is an exact slope field for this problem. So I'm gonna actually pull that up. Let's see. Here we go. Get this in view. All right, so when we're talking about slope fields, this is the same problem that we were just working with. And this is a slope field that was made with computer-generated software. So obviously not done by hand. So the part that we captured was just right here in the middle of it, from -2 to +2, basically. So that's really what this slope field should look like. So again, this slope field is showing us what the solutions, like what multiple solutions would look like for this differential equation. But let's say that we have a particular point. You'll see this on the next page of the spiral, but I'm gonna just try to show you how we could trace this. In the past, we've seen some FRQ questions on the AP exam like this where you actually have to trace your slope field. So let's say that we have the point 0, 2. And so if I go to my graph and I plot 0, 2, if I kind of try to trace, like follow the direction of the slope, I can see that it's getting steeper, 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 steeper. I kind of trace that curve. And then as I come out on the other side of 2, my slope is getting more and more shallow. And then as I kind of follow it backwards, it gets kind of, looks like it kind of gets sucked right into that curve there. Oh man, this is hard to do on this computer. All right, so you know what, I'm not gonna put arrows there, but that's what that would kind of look like. All right, so that could be a solution for the particular condition of the point 0, 2, for that point. We could look at another one. Let's see if I can use a different color. Let's say that we were over here on the graph. Let's say that we're at -2, 0, for example. As I kind of follow from that point, as I kind of follow the curves to the right, you can see it gets steeper and steeper as we go down. And as I go to the left, kind of gets sucked in there. So that curve, again, it looks very different from the curve above it. We could do a couple of more points, but what I really just want to point out to you is if we go to this next page, on page 115 in the spiral, you can see a couple of different points that are traced through the slope field. So you can see a visualization of different solutions. So even though we are not going to learn how to solve that particular differential equation, we can picture what some of the solutions look like. So please do read the text through this paragraph. I'm not going to read the whole thing to you, but please make sure you read the text through this paragraph at the top of page 115. And then afterwards, there's going to be a little matching activity where I'm going to have you try to match some slope fields to some differential equations. So you might want to make a table and try to do it kind of like I modeled for you, but that's going to be the next activity.